So
no, Raph, don't pour water on the sun. Don't do it.
Hey, so we're recording now. Welcome to our lab portion of this course. We are going to attempt to measure the masses of a famous binary system called AS1020. Now, today's lab is going to be a little bit more mathematical than we're used to.
Yay.
I know. It's not too crazy, but it's going to be a little bit of formulas and punching. I'm going to try to help relate it to the theory from our class as well. So I need to give you guys a teensy bit of a preamble here before we get going. And let me go to speaker view for that. And let me talk to you about the purpose of binary stars. So as I will eventually talk about in this class, 50% of all stars that you see in the sky are binaries. The reason why you don't know that they're binaries is because most binary star systems are unresolved, and they appear just as a single spot of light.
Close to
Now,
height.
I'm sorry, Riker?
No, somebody sneezed.
Oh, is that what that was? Okay.
Yep.
Now, there are two different types of methods that we can use to study binary stars. Sorry, I'm losing focus here, okay? There are a class of binary stars called eclipsing binaries, and there's a class of stars called spectroscopic binaries. And these are basically just two different techniques or two different methods of studying binary stars. In both cases, the star is a single star that you know actually is two stars orbiting around each other, but you deduce that there are two stars by studying something called their light curve and then something called the Doppler shift. So eclipsing binaries you study by measuring the brightness of a star, you measure the light curve, and the spectroscopic binaries you measure by using the Doppler shifts to get the velocities of the stars. But in either case, whether you study your binary star as an eclipsing binary or a spectroscopic binary, the point of a binary star is always the same. The point of a binary star is you can use them to find the masses of the two stars. And do you guys remember what famous formula we use in astronomy to measure masses in astronomy? There's just one formula that we have at our disposal that allows us to find the masses of stars. What is that? Raph, E
No.
equals MC squared is not the answer. Oh, okay. I thought someone might remember. The cosmic balance beam, as it's known. Anakin, do you know? Can you tell us? If I pick on you, Anakin?
NK3, maybe?
NK3 is the correct answer. NK3.
Nice.
By the way, Anakin, you have the power. Okay. Thanks, Anakin.
Oh, Anakin, hard with the correction.
So anyways, so the people at home who are watching this later can't see the chat log, but the chat log is really funny. I've been trying to save them with each of the video files. They're hilarious.
It's really just Raph.
It's just Raph, just bombing everyone. Okay, so listen, there's a simplified version of NK3 that you guys had not earned the right to use up until now. I'm going to show you something called NK3, the Kiddie edition. The Kiddie edition is going to allow us to calculate the masses of stars quite simply. And it goes something like this. The total mass of our system, which is the combination of star 1 and star 2, is just simply a cubed over p squared if we use the following Keplerian units. All semi-major axes should be measured in astronomical units. All periods will be measured in years, and all masses will be measured in solar mass units. And this is the point of binary stars. Binary stars let us find the masses of stars. Remember that the cartoon picture here is you've got one star, M1, and there's another star, M2, which is orbiting around it on a circle, or a quasi-circular orbit. And the separation between the stars is A, their semi-major axis of revolution. Okay, so much by way of review. Now, I'd like you guys to take a look with me at the binary star lab, and I'm going to show you how this thing's going to work here. So let me go to share screen mode. Let's exit out of this. And let's see if I can find today's lab here. Just get rid of the Fisher cat. Okay. So guys, follow along with me in your lab books if you can, or on a computer screen. I want to show you a cartoon of how a eclipsing binary star works. Let's say that you're just measuring the light from a single star, but you suspect that there might be a binary star there. If you should be so lucky that one of the stars orbits sometimes in front or the other, in other words, if you happen to catch the binary star edge on, everyone look at my two markers here, pretend the red and the blue are stars. This is a binary star which is measured edge on, where the stars will sometimes pass in front of each other. Another option is that you might see them face on. If you see them face on, you're screwed because you're not going to be able to measure Doppler shifts or eclipses. But in those situations where one star eclipses the other, here's what's going to happen. Let's start by considering configuration 2. In configuration 2, the two stars are side by each. And remember that you're just measuring one single star, one pinprick of light on the sky. But that one pinprick of light is the combination of the photosphere of both of these stars. That's when your light curve is going to be at a maximum, and you will measure the maximum flux or brightness from the star. From time to time, one of the stars might dip behind the other star. And that's when we lose one of our star's photosphere's contribution to the brightness. That results in what's known as a primary eclipse, where you get a big dip in the light curve. It's also possible to get a secondary eclipse, where the small star passes in front and just reduces by a small fraction the amount of light you get. We're going to be focusing on the primary eclipse of a famous binary star known as SS Boötes, or SS Boo, shown right here. And these were taken with a 16-inch telescope, just like our telescope, except, of course, they were in the much darker skies of Tucson, Arizona. Now, we didn't quite get to the spectral types of stars today, but one star is similar to our sun. It's a G-type star, and that means it's kind of a yellowy hot star. The other star is a red giant star called a K-type subgiant, and that means it's a big fat red star. So for the purposes of simplicity, let's assume at the beginning of our discussion here that we have a small hot star and a big cool star. I'm going to represent the hot star like so. It's going to be a smaller but hotter G-type star. And I'm going to represent the red giant like so. It's going to be a big fat cool star. So we're going to refer to our two stars as the cool star and the hot star, because remember that we can easily measure the temperatures of stars based on their color. All right, let's take a look at the primary eclipse. This is the moment when the hot star, the G-type star, is about to disappear behind the larger, cooler red giant star. Let's go back to our lab here for a second. Here's a cartoon of what the primary eclipse is going to look like, and then we're going to do some work on it. In configuration A, the stars are side by side, and we'll get the maximum amount of light from them. Now, you might think, well, Brendan, you're just measuring the brightness of the stars here, and that is true. But remember that essentially both stars in the binary component are roughly the same distance from the sun. And that means while the quantity that we might be measuring is the brightness, that brightness is proportional to the luminosities of the two stars, because the difference in distance is not significant. In other words, a direct measurement of brightness is an indirect measurement of luminosity. Did that statement make any sense? Because I could try to explain that better. All right, I'm just going to assume the answer to that was no. Look at your inverse square law, right? In the inverse square law, if both of your stars lie at the same distance, then the distance is constant. Brightness is then proportional to luminosity. And a measurement of brightness is the same as a measurement of luminosity. Anyways, I think that's the best I can do with that. In configuration B, we hit something called first contact. That's when the small hot star is about to disappear behind the red giant. During the time that the star is slowly moving behind the hot star, the red giant star, the light curve. Pardon?
If I may interrupt real quick. But so basically this, so the light is at 1.0, so that's the brightness we generally see at points A, B, F, and G. But at C, D, and E, the brightness or luminosity goes down because one of the stars is now hidden behind the other.
Right, but here I've normalized the luminosity. Do you know what I mean?
No, that's just, yeah, no, that was just a figure to utilize, but.
Yeah, because the actual brightness you might be getting from them might be 4.5 times 10 to the minus 10 watts per square meter. But no one wants to work in units like that because that sucks, right?
Right,
So instead,
one worked fine.
Yeah, that means you're getting 100% or the maximum amount of light you can from the binary. And here's a percentage dip in the light source. Now, Riker, do you understand why this slanted line is slowly going down here? Why is there a diagonal here? That's what I want to see if you guys understand.
It's a diagonal because it doesn't just touch and then instantly disappear. It's still slowly going behind there.
Right, and you're losing photosphere. Now, that turns out to be kind of interesting because we can use the difference in times to estimate the diameter and therefore the radius of the star. Hear me out on this, okay? If I can see my star slowly going behind the other star, and I can measure the difference in times, the difference in time from this point to this point, that delta t is a measurement of the diameter of the star. For instance, if I knew the velocity of the star, which I'm going to get in the next section, I can multiply delta t times velocity, and I can get the diameter of the star. I can also get the diameter of the star by measuring the time difference from first contact to third contact. Because from first contact to third contact is the time it takes the front of the star to go from here in configuration B to here in configuration E. It's going to cross the diameter of the hot star.
Right.
So what we're going to be hunting for...
It'll cross the diameter of the cool star.
Geez, Riker. Thank you. I was just testing you to make sure you were with me. That's good.
See, I hadn't eaten yet. That was the problem.
Yeah, okay. Well, I haven't eaten yet. That's my problem.
So first contact to second contact gives you the diameter of the smaller, hotter star, whereas second contact to third contact gives you the diameter of the larger.
Hold on, Riker. I thought the same thing the first time, but hold on. We've made an error there. It's not second contact to third contact. It's first contact to third contact. Look at my notes on the board. Imagine you measure from the start of the star here. That's first contact, right?
Right.
If you want it to cross there, this is...
Okay.
Right?
Yep, nope, I got it.
T1, T2, T3. You've got to go from first contact to third contact to get the... Do you see that now?
Yeah, I see that now.
Okay. One other thing, and then we're ready to start working here. During the time that you go from second contact to third contact, only one of the stars contributes to the luminosity of the system. And that's the bigger, colder red giant star, right?
Yep.
Between these 2 points, only the big fat red star is giving us any light, correct?
Yes.
Let's start this game by looking at the real data for SS Boötes, okay? And let's see how we can get the relative luminosities of the stars and the relative radii of the stars just by playing around with some of these numbers. Okay, let's look at real data. Cartoon time is over. On the figure that you see here, which is 14.7, this is a real measured light curve of the famous star SS Boötes. And you can see that some graduate student slave has been toiling away throughout the night collecting data points of the brightness of the star. They're just looking at one single star, but the graduate student slave has been up all night while we were eating Cornish game hen at our luxury apartments. The graduate student has been out at night in the cold, collecting these data points and gathering the light curve. And then we've even made the graduate student plot it up for us and draw a best fit curve showing a nice light curve here of what's called a primary eclipse, okay? Now, at this point, I want to switch over to work mode with you guys. So you're going to have to bear with me here, class. I am going to sort of twist my computer sideways and point it down at the desk. And this, unfortunately, yes, Zoom sucks, but this is one of the reasons why we still need to use Zoom until I can figure out a better system. Zoom has this iPhone feature that we just cannot go without for the purposes of these labs. So I'm going to share screen. I'm going to choose my iPhone. Okay. There's Zoom. And now, boom. We've got our moving workstation here. I'm going to activate a light source. Okay. So now I've got a little light source. And we're going to need a ruler for this, okay? And we're going to need a very sharp pencil. So let me sharpen up the pencil.
Ruler.
Okay. Okay. And we're going to need a roll of tape to serve as my iPhone stand. All right. So you guys with me? Can you see what's up here?
Yeah.
Thanks. So let's go to our primary light curve here. All right. Now, class, if you're working at home with me, you can follow along and you can do this lab with me. All you're going to need is your handout and a ruler. Okay, let's try to decide where we think the light curve kind of starts. I'm going to say, because these are the data points, we should never go by the individual points. We should always go by the line itself. And I'm going to say the first dip, oh, this is a tough one here. Class, what do you think? Should we choose there or should we choose there?
The 7th.
This one or this one? Riker, what do you think?
The first one.
Here?
Yeah.
All right, hold on. I'm with that. Let's follow that down. Okay, here I've got to make sure I don't screw this up. So it's very easy to drift by a box. Okay, and geez, that's so barely light. I don't even know if you guys can see that. Whew. Can you guys see that?
Yeah.
All right.
Yeah.
That's our T1, right?
Yeah.
Okay. That's our first contact. All right, let's draw in our second contact together. Let's get some more thoughts here. Where would you say it bottoms? I would say it bottoms out maybe there. Is that what we want to choose?
Yeah.
There?
Yeah, that's what I would say.
All right, so hold on. we're all going to kind of choose the same ones together. That way this doesn't get too crazy, okay? So that's our T2.
Got it.
And now we'll go to T3. You guys like that?
Yeah, that one.
Okay.
Yep.
All right. Okay. Thanks for the inputs. All
Got your
right.
back.
Whoop, you got my back. Okay, and that's T3.
Yep.
And let's do one more thing here. Let's get the luminosity too. Okay. So following along, let's go across the bottom and find that intersection there. Okay. Now, if you guys could have the SS botes side by side with your data sheet here, okay? And this is the sheet you're going to be turning into me. So let's make sure we get our name up here.
Wait, are we only turning in that sheet?
Yeah, that's the only sheet that you need to turn into me.
Oh, geez. Okay.
Just the data sheet, not the graphs, because I'm doing this at home and because I don't have a printer. So drawing
That's
out.
fine. You don't need to turn in the graphs. But I just wanted you to print out the graphs so that we could kind of draw this stuff together if you were following along with me. Don't forget to put your section on there as always, whichever class that you're in. I think Emily was with us too earlier, right? Emily, you still there?
Yeah.
Yeah, I'm here.
Okay, cool. It's nice to have some night people join us.
Wait, so we don't need to turn this in?
Not the graph, but the
Graph.
Okay.
You need to turn in 14-9, okay? That's what we're going to turn in. All right. Notice our first job is to get the relative luminosities, the luminosity of the cold star, the giant star, and the luminosity of the hot star. Now, which luminosity does this represent down here?
that
Do you remember?
represents the mass of the larger, cooler star.
The luminosity, you mean?
Yes.
Okay, so how do we figure out what that value is? Look, can we talk about a useful skill, students? Something I like to teach my students. You start with two printed
Yep.
numbers, 0.6 and 0.5, and you find the interval. What is the interval between those two? What's the interval?
0.55.
Sorry?
Is it 0.55?
No. The interval is, oh, I see what you,
Point
can we,
one.
Emily, can we just do this slow and steady by the numbers? What's the interval between these two big boxes?
0.1.
Thank you. That's 0.1% luminosity units, right? Random luminosity units.
Oh.
Now, how many boxes are in between? You count the boxes.
10.
Okay. So that means if you do 0.1 luminosity units by 10 boxes, what is each tick worth?
0.01.
0.01 luminosity units per tick mark, right? Okay, so Emily, what did you say this one was then? You said 0.55, but I disagree. Because
0.58.
here's 0.5. What's this next one here?
0.51.
0.52, 0.53, 0.54, 0.55, 0.56, 0.57,
0.58.
0.58. So that's the luminosity of our cold star right there. There's no units, they're just arbitrary percentages. What would then be the luminosity of the hot star? Remembering that we've normalized it to 1. Doesn't this top here represent the luminosity of the cold star plus the luminosity of the hot star?
Right, so it would be 0.42.
Right, because LH plus LC have to equal 1.0, right? So if we subtract 1.0 minus 0.58, 0.42. So which is more luminous? The cold star or the hot star?
The colder one.
Hey, Riker, I don't know if that makes any sense to me. Why would a cold star, a cooler star, be pumping out more light than a hot star? How's that possible?
They're going to be coming from A. Last 3.
Huh. Is that weird?
Does it have to do with like the visible light spectrum?
Okay, hold on.
Because of the size of the stars.
There you go, Marcus, because of the size of the stars. Let's everyone try to understand what Marcus was just saying there. Hold on. Where are we? It's something called the Stefan-Boltzmann law for stars. We'll talk about this next time, but let me just find it for you here. Just a second. Look at this slide here, slide 56. If both stars are the same size, the hotter star will clearly be more luminous because stars glow like black bodies and temperature controls their light output. But if the stars have close to the same temperature, but one star is a big fat star, that star can be more luminous just because it's bigger and there's more square meters of surface to radiate away light. So there's a confound between temperature and radius, right? In our case, in the case of our star, the radius has won out over the difference in temperature. Does that make any sense?
Yes.
Yes. Even if it's not true. All right. Now let's get our times of first contact, second contact. Students, use my methods. Let's figure out what each tick mark is worth here. What is our interval? What's our time interval?
0.2.
Okay. Now, do you guys notice that they're using Julian days? That means the Julian calendar. Any idea why astronomers might prefer Julian days to our modern Gregorian calendar? Does anyone from Astronomy 1010 remember the difference between the Gregorian and the Julian calendar?
There's no leap year.
That's right. Michael, why would astronomers prefer to work without leap years?
It just makes the math easier. Raph says because it's a lot more accurate.
Well, no, it's not about, I think your first answer was better. Leap years
No,
would,
I was just saying what Raph said.
if you have to
just makes it
consider
easier.
leap years, the time intervals over things will become more complicated, right? Astronomers actually prefer the Julian calendar to the Gregorian one. Anyways, whatever, I'm rambling here. So there's 0.2 days is my interval. How many boxes do I have, students, in between there? Count the boxes for me while I sip iced tea.
1, 2.
20.
20 boxes. So we have 0.2 days.
Dude, I was counting. I swear I thought the shaking was a secret.
What is each tick mark worth, students?
0.01.
Yeah, it just happens to be, sorry, 0.01 days per tick, right?
Yep.
Okay. So what then do we measure for T1? What's the tick mark before 331.8 equal to?
0.04.
What?
0.04.
No. It's a hundredth per tick, right?
Oh, 0.004.
Oh. Hold on. Riker,
Am I screwing that up?
I just want to make sure that we can count ticks properly. If this is 331.8, what is this tick here?
331.79.
Thank you. What's this one?
331.78. 331.77. 331.76.
And that's our T1, right?
Yep.
Is everyone with me here? I don't want to lose you guys.
Playing the Wii Shop channel music.
Wait, say that again, Michael?
Who was playing the Wii Shop channel music?
Not me.
I can.
All right. Know that I heard no. Just I heard it, whoever you are.
All right, all
I
right.
heard it too.
Are you guys still seeing my? What are you guys seeing right now?
T1331.76.
Oh, you're seeing this? Hold on, Mike.
Yeah.
I want to be able to see just what you're seeing. Okay, all right. There we go. Okay, so let's get T2. Class, use your skills. What's T2 right there? Anyone? Come on, you guys. I'm growing old and I'm dying here.
331.95.
Thank you. This is 332.00. That's 99, 98, 97, 96, 95. Thank you, Riker.
Right, it's so messed up.
How about T3?
Three three one. 332.15.
Yeah. 19, 18, 17, 16, 15. Have we all got that?
No.
How can I help, Morgan?
1 second. Hold on.
Never mind, you moved it.
All right. See this? Radius of the cold star, right? We got to get this from our formulary here. Now, see if you can follow me on this. You're kind of going around in a circle there, right? So the radius of the, the radius of the cold star is pi times the difference in time divided by the period. The idea is that the ratio in the time lag over the period is the same percentage as the radius versus the semi-major axis of orbit. And the period for this binary is always the same, 7.60614 days. So let's get our calculators out. Oops. Let's get our calcies out. And we've got to do T3 minus T1 times pi over the period. So, let's
332.15.
T3, yeah, 332.15, right?
Times pi
Minus
divided by
331.76
7.6
equals times pi divided by 7.60614. Is that what you got, Riker?
Nope.
What'd you get?
I got 195.12.
Did you use parentheses like the big boy told you? Did
No,
you
I
use
did not.
Did you use
No, I did not. No.
Then that's why you got it wrong. Let's do it together, okay? Pi times open parentheses 332.15 minus T1 331.76
Fuck.
close parentheses divided by the period, which is 7.60614. Did you get that now?
Hold on.
Yeah.
Morgan, you got that?
Yeah.
Cool.
Okay, now I got it.
All right, so that's the radius of the cold star. Let's just round it to 0.16. And does anyone know what this 0.16 means? It means 16% of the semi-major axis. In other words, we're watching the star go around in a big loop. And for a fraction of its loop, it's disappearing behind the hot star, right? Or behind the cold star. So it's what percentage, this percentage here is 16% of the entire semi-major axis. Whatever. Let's just call it scale radius, okay? It's 16% of the orbital radius. Let's do radius of the hot star. It's the same thing, but this time it's T2 minus T1, okay? So our T2 is 331.95. Well, actually, we'll do pi times, open parentheses, 331.95 minus 331.76, close parentheses, divided by, 7.60614. Anybody else get that?
I didn't get that, but I got
No.
I got roughly the same if we go by 2 sig figs.
Did you use the pi key or did you use 3.14?
I used pi.
Then why wouldn't it be exactly the same? We all have the same numbers, right?
I got 0.0826.
Right, let's punch together. Pi times, open parentheses. Are you using 331.95?
Yes.
Okay. Minus 331.76. Right? Close. Divided by 7.60614.
What am I doing wrong here? It's T2 and T1. That's okay.
Is anyone else getting the number that I got?
I got that.
Yeah, I got that number.
Okay. So Riker, check yourself before you calculate or wreck yourself. Let's just round that to 0.08. Then we're all right. The hotter star is only 8% of the semi-major axis. So it's 16% and 8% of A, the semi-major axis. We don't know what the semi-major axis is yet. We'll get that later. Can we move on?
Yes.
All right. Now we're going to turn it over to, we're going to start looking at the eclipsing data. And for that, we're going to use the Doppler shift. I can't remember if we had a lecture on the Doppler shift or not. I remember doing it, but it could have been that it was from last year or something. Oh, let's let Zach into the waiting room. Just give me a second here where I share my screen with you guys. I want to share my screen, and I want to show you a picture of spectroscopic binaries so you can understand how we use the Doppler shift to do this. So down here, okay. So we've got a pair of binary stars, 94. And even though they're probably on, Keplerian ellipses, let's just pretend that the orbits are quasi-circular. That'll make things a little bit easier, okay? In the Doppler shift, here's what's happening. Remember that stars produce absorption spectra. They give us absorption lines. And the two absorption lines you're looking at in your cartoon here are probably hydrogen alpha and hydrogen beta. You are represented by the little green dot here on Earth. And the binary star system is over here wiggling towards you and away from you. There's a small hot star and a big cool star. The colors have been reversed here because I found this on the internet. And when one of the stars moves towards the observer, the Doppler shift produces a blue shift. And that's when the absorption lines shift towards the blue end of the spectrum. When the star moves away from the observer, you're getting a red shift, and the absorption lines are shifted to the red end of the spectrum. The larger star has less velocity because its mass is making it more sluggish, and it's also going through a set of blue shifted and red shifted absorption lines, just not quite as much. And if you remember anything about the Doppler shift, you'll remember that the purpose of the Doppler shift is to get the velocities of the stars based on the shift in these absorption lines. So let me go to my share screen again. Let me share my iPhone. Just a moment here, it's loading. What's funny, Michael?
Me.
Oh. All right, hold on, that didn't work.
Yeah, I dropped some pretty good jokes in the chat.
Oh, come on. I shouldn't have shut this thing down. Now it's going to be cranky on me.
What was in the mailbox, Tom?
You're not hiding it? You didn't steal it? Your ass is big enough. No, it does. Your ass.
What?
Okay, hold on. My Zoom share is actually troublesome here. Let me close all my other damn apps. Let me try this one more time. I don't know, Sal, is that you or me? That's not me. I don't know whose background chatter that is. All right, let's try this again. Waiting for this thing is the most stressful part of these classes because sometimes it just doesn't load. I'm sorry, guys. Bear with me. Let me try a boot here. Cycle power.
Nope. I'm gonna do one more, please.
Anyways, here's something I can do while I wait for my stupid fucking phone to reset. Let's go to my share screen again, and let's take a look at our binary star lab. On the next page here, let's look at the cartoon version of this first, okay? The cartoon version is shown here in this figure B, where you can see the two stars. There's the A star and the B star, and I believe the A star is the more massive one. And what you can see is, you can see that if you measure the velocities at all of the different points, so you measure the velocity in configuration 1, the velocity in configuration 2, 3, 4, you can produce something called a radial velocity curve. This is where the star becomes positive, or it's, usually you define positive red shifts as away from the observer on Earth, and blue shifts are negative towards the observer on Earth. Sorry, guys, I'm trying to talk to you and boot my phone at the same time. It's irritating, okay?
It's
Now,
okay.
if you imagine a couple of binary stars orbiting around you, you would naively expect that all of the red shifts and blue shifts would be positive or negative, okay? So So when a star is moving, the binaries are doing this, right? When a binary moves towards the observer, it's being blue shifted. When the star moves away from the observer, it's being red shifted. When the stars are moving perpendicular to the observer, there is no red shift at all, because red shifts only work along the line of sight, okay? They only work radially towards or away from the observer. So if you plot all these velocities, you should get a star having a negative velocity when it's towards you, a positive velocity when it's away from you, and then it should have no Doppler shift at all when it's side to side. But if you actually look at the spectroscopic data from our binary system, and here it is here. So here's the actual red shifts and blue shifted data with some lines drawn into them. Now the filled circles represent the cool star, the red giant. The open circles represent the hot star, which is the small G-type star. And you'll notice that instead of having the velocities be positive or negative, the velocities seem to orbit around negative 40 something here. We're going to figure out what that is in just a minute. What does it mean if instead of the velocities orbiting around 0, the velocities orbit around negative 40 something? It must mean that the entire binary star system is not stationary, but the entire binary star system has a negative velocity and is actually moving towards the observer in space. So before we can get their velocities, getting their red shifts and blue shifts, we're going to have to subtract out the component of velocity that's responsible for the stars moving towards the observer. And how are we going to do that? Well, I'm going to show you if my phone will just allow me to Zoom with you. Let's see if I can do it now. Stop share. Share screen, iPhone. Okay. Moment of truth, everyone. Yes. Okay. Just want to kind of point my camera down at the table where I'm working here so you guys can watch me. Here we go. Okay. So let's get our light curve data out. I mean, sorry, our velocity curve data out. You guys got that page handy? The first thing that we're going to need to do is we're going to need to see the center of mass velocity. So you guys will notice here, if you look closely, the center of mass velocity, the velocity between the two stars, is not quite at the negative 50 line. It appears to be somewhere in between this box and that box. Let's try to draw this in here with our ruler. So I'm going to take a ruler, I'm going to make it dead in the center of these two. I'm not going to bias it towards a line. Okay, I did bad. I've got a tiny bit of drift here, so let me try to redo that. I'm gonna see if I can do a better job here. Let me go sideways. There we go. Okay, this is what the book calls gamma. Gamma is our center of mass velocity. Let's go and figure out what our velocity tick marks are worth. So these velocities are being measured in kilometers per second, right? But what is each box worth in terms of its kilometers per second? Let's take a look at an interval. What's our interval here? From negative 100 to 150, what's our interval?
50.
Okay, and that's 50 kilometers per second. How many boxes are in between that?
10.
So what's each box worth?
5 kilometers a second.
Per tick mark, right?
Uh-huh.
5 kilometers per second per tick. So then Riker or Morgan, what would you estimate this center of mass velocity line to be at?
About 47.
Negative 47. I like that. Let's go with that. It's a little bit. Good job. All right. Let's see here. I need you guys to do something weird. Now, this distance from here to here represents the magnitude of the velocity of the hot star when it's moving away from me or is redshifted. Here is the velocity of the hot star when it's blue shifted. So I want you guys to do this. We're going to look at phases at a quarter phase and at 75% of a phase. So this is 0.2. That's 0.2224, and 0.25 is right about there. And right at 0.25, I want to draw a line in that goes from the top to the bottom of this curve, but not further. See that? Notice that I did not go above or below that curve. You guys can follow along with me. Now this represents what they're going to call alpha hot. Wait, is the filled circles, shit, represent the cooler star. Sorry, guys. That's alpha cold. Alpha is the redshift, okay, alpha cold. And then the betas will be used for blue shifts. This is beta hot, okay? We're going to do the same thing at 0.75. This is 0.7, 0.72, 0.74. There's 0.75 right there, okay? Let's do this nice and careful. All right, so this is the hot star now. This is alpha hot. And this is beta cold. So let's look at that again. We have alpha cold, the redshift of the cold star, beta hot, the blue shift of the hot star, alpha hot, the redshift of the hot star, and beta cold, the blue shift of the cold star. You guys got all that? That's a little bit much. Alpha cold, alpha hot, beta cold. Copy all that down if you're following along with me. Let me use my clicker here.
Hey,
I'm going to hide non-video. Shoot, I can't do that, can I? I don't like how you don't have, oh, here we go. Video settings. I want to hide non-video participants because I can't see what you're doing anyways. So at least if I can see the video people, I can see if you guys are following me or not. All right. Now, look, if you want to just watch the show, you can watch the show. If you want to follow along at home, that's, of course, better, but I'll leave it up to you guys. Okay. We've got to estimate these values. We've got to estimate alpha hot, alpha cold, beta hot, and beta cold. Now, these quantities are intervals. Does anyone know what I mean by that when I say an interval and a number line? What the shit is an interval? This is an interval, right? If I am between 16 and 18, 16 and 18 are numbers, but my interval is 2 centimeters. Do you see what I mean?
Yeah.
That's what I mean by an interval, the distance between 2 points. So alpha cold is an interval. We can see the bottom point here is what Riker told us was negative 47. Okay. What's the top value seem to be at?
25.
Okay, so what's the interval? If we go 25 minus negative 47, what do you get?
72.
Yeah. Watch how I type this in. 47, then the negative, and then equals 72. So that's our alpha cold. Let's get our alpha hot now. What do you think your alpha hot is? Oh, I might have to go sideways on this. I don't know. Hold on. If I turn off my lock screen and I go sideways, what happens? Oh, yeah. Now we're talking, doggy. Why didn't I ever figure this out before? This feature rules. Okay. So what's our alpha cold, our alpha hot, I mean? What's the top?
Negatives. Our alpha hot?
Well, what's this value up here?
That's about 24, about 23, 24.
No. Well, hold on. It's what fraction of a box is that?
They're not like close to 25.
Right, but
It's
each
just under.
box is worth 5, right? Look,
Yeah.
let's do a zoom in here. The box is like this, and the bottom of it is 20, and the top of it is 25, and the curve is like coming up like this.
So 20 point. No, actually.
It's 43.
Yeah, it's like 23, 24.
Yeah.
Let's say 23s.
Okay.
Oh, sorry, Riker. I guess 24. It didn't seem like it was quite 24 to me. You know.
It might be because I see your line there. That might be skewing it, but
Yeah, that's probably
Yeah,
that's why
23.
we want to go above and below. There we go.
yeah, that'll do it. Yeah.
So 23 minus, oops, 23 minus negative 47, right?
That's 70.
That's 7. Okay, that's. Now, the nice thing about the betas is that the betas actually do seem to end at the same line here. There and there. And that's negative 125, okay? Normally, when you do an interval in your algebra class, normally you subtract the top number minus the bottom number, y2 minus y1, correct?
Yeah.
But in this case, we don't want to do it that way. We want to get our velocities relative to the center of mass so that basically our red shifts come out positive, but we want our blue shifts to come out negative. This is something that I had to learn through trial and error. There's no reason you would have known that beforehand. So instead of doing negative 47 minus 125, let's do minus 125 minus negative 47. What's that give us?
Negative 78.
That's right. Let me just confirm that. 125 negative minus 47 negative. Negative 78. And that's going to be both beta hot. Whoop. That's going to be both beta hot and beta cold because they both have the same trough. This is the most confusing part of this lab right here. Well, one of them. Okay. Now, there is a well-known rule in binary stars. In binary stars, the ratio of the velocities is the inverse ratio of their masses. And that means the little star with less mass gets flung around faster, and the heavier star gets flung around less because it has more inertia. Let's look for this formula here. The formula is, and you got to use parentheses, the ratio of the hot mass to the cold mass is alpha cold plus beta cold over alpha hot plus beta hot. And here we have to be careful to include the negatives, okay? So I'm actually going to get a little pad to write this out in. That's going to be helpful for us. Bear with me, class. I'm going as quick as I can. It's kind of awkward. I've never done this over the internet before. Okay, so the ratio of the hot mass to the ratio of the cold mass is alpha cold plus beta cold over alpha hot plus beta hot in parentheses, okay? So our values are here, just above, so we'll plug them in. Okay. That's equal to cold, alpha cold is 72 plus the beta cold is minus 78. Okay. And that's over the hots. So 70 essentially minus 78. Okay. So let's do
So
that.
it comes to -6 over -8.
There's not infinite precision here, so we should not use a fraction. What's the percentage?
0.75.
Okay, that sounds better because that's not. Do you know what I mean, Riker?
Yeah.
6/8 has infinite precision, but 75% has two significant figures. Does that make sense?
Yep.
Our measurements are not infinitely precise here, so we should not use a reduced fraction or whatever the hell they call that. Everyone, sorry, 0.75.
75.
Sorry, Morgan. Okay. Everyone got that mass ratio?
Hold on.
Yep.
Hold on one
Nope.
sec.
Sure thing.
Marcus, I like your hair in your photo. It's very swooshy.
Thank
You're welcome.
It was because I dyed my hair and then all of it left, and it like left my hair with like a rusty color. Also, that photo is mad old, so like
One, I figured.
OD procrastinating.
Okay, how you doing, Marcus? Are we ready to move?
Yeah, we good.
How the rest of you doing? Frank, Michael, Ivy, you all with me? Emily? Okay.
I'm great.
So, oops, my phone just went to screensaver mode here. All right, so let's move on here. Now look, now comes the big kahuna. Oh, we have to get the total relative velocity. Here, the book made a major error. If you keep track of your negatives, it's supposed to be alpha hot minus beta cold. But there's something I don't like about this. Do you guys see how alpha hot is actually less than alpha cold? If you think about the velocities here, you've got one going up and the other and going down, and the other one's going down and then up. The greatest relative velocity should be the maximum of whichever star is the maximum minus the minimum of whichever star is the minimum. That should be your relative velocity. So not only are we supposed to be subtracting these, but they said alpha hot minus beta cold. And I don't like that because alpha hot doesn't sample the curve as high as alpha cold does. So we're going to change this, and we're going to say the relative velocity, an improvement formula, will be alpha cold minus beta hot. That's the stars at their maximum and minimum, which is 72 minus -78. What's that give you, kids?
150.
You guys follow that logic there? Maybe that might have been a little fast and loose for y'all. I want to sample the curve at its, oh, they have it right here, kilometers per second, at its maximum and minimum peak. Now it's time to get our semi-major axis using our legendary binary star formula. And here, you'll remember if one of our stars is going around in a circle, right? We did this last time. And the radius of the circle is A. The circumference of the star is 2 pi A. That's its circular orbit that it's going around. But if it travels at velocity v, and if one orbital period is p, then distance equals rate times time tells us that it should travel around the circumference at this velocity times p, the period of observation. And I can use this to solve for A, the semi-major axis, and get something called the binary star orbit formula. The binary star orbit formula is a way to calculate the semi-major axis of the star's orbit without having to resolve it or see it, provided you can get the velocity. It's velocity times period over 2 pi. Normally you would do this all in MKS units, but here our units are totally whack and totally effed up. We've got kilometers per second here, which is not MKS. And our P is being measured in bloody days. You'll remember that the period of this binary was 7.60614 days. So we're going to have to do a couple of conversions here. We're going to have to multiply this times 0.211 over 365.25. The 365.25 will convert from days to years. And the 0.211 will convert from kilometers per, sorry. It'll convert to AUs per year over kilometers per second. Now I could prove all that if you really want me to, but don't make me do it, okay? Just trust me. 0.211 is the conversion from AUs per year to kilometer per second. And 365.25 is the conversion from days to years. Y'all with me?
Yep.
Probably not. Okay.
Yeah.
Anyway, we've got our velocity here. Our velocity is 150 kilometers per second, right? And we've got our period here, so let's plug it all in. So our A is going to equal, the velocity is 150 kilometers per second times the period, 7.606. Let's just use 7.606 days. Hell with the precision, okay? Over 2 pi times 0.211 AUs per year per kilometer per second, all over 365.25 days per year. I know, that sucks. Can you guys just do this for me though? 150 times this, times that, divide by this, divide by that, divide by that.
0.1.
That's what I think I'm going to get too.
That's what I got.
Yep. So our A is, and what are our final units? See if you can figure that one out.
Days cancel out, years cancel out.
Astronomical units.
Excellent. And that's what we're going to write here.
Where'd my pen go? There.
Okay. Y'all ready to do some NK3 Kitty Edition? NK3
Yeah.
Kitty Edition tells us that the total mass of my system is A cubed over P squared. Okay? Where A is in AU and P is in years. My A is 0.1 AUs. My P is 7.606 days. So I'll plug it in as M total is 0.1 cubed divided by 7.606 days over 365.25 squared. So let's plug that in, all right?
Bless you.
Thank you.
0.1 shift cube divide by, open parentheses, 7.606 divide by 365.25
0.3.
squared. Yeah. And what are your units, Morgan? What do the units come out to be in the Kitty edition? It's a magic formula. You either know it or you don't.
It's the M with the sun thing.
Solar mass units.
Solar mass.
Morgan, you are on fire today. Very good. 2.3 solar mass units. We're almost done, students. Bear with me. You guys all caught up to me?
Yeah.
All right. Now they want us to find the individual masses, and that's a little bit tricky. This is a game called Two Equations, Two Unknowns. See if you can follow my calculations here. I know that the mass of the hot star plus the mass of the cold star have to add up to 2.3 solar mass units. But I also worked out earlier in my mass ratio that the mass of the hot star divided by the mass of the cold star, the hot star is 75% of the cold star. So this is a game called Two Equations and Two Unknowns. The first thing to do is to multiply MC up there to get MH is 0.75, 75% of the cold star. And now I can take this MH and I can plug it in over here, okay, to get this formula. 75% of the cold mass plus the cold mass equals 2.3 solar mass units. Here's the moment of truth, class. What should I do next to deal with this? What's my next step? Who knows algebra?
Subtract 0.75 from 2.
That won't do any good, Marcus, because you'll still have the MC flopping around with you. Then we'll have MC on both sides of the equation. I don't like that.
true.
Did someone say YouTube?
I said true.
Oh, true.
Yeah,
Divide
What do
by
I do,
0.75
algebra lovers?
divide 0.75 on both sides.
That won't help you, because you'd have to divide it by all three terms.
Take out the MC.
Oh, factor out the MC, Morgan?
Yeah.
You're a genius. So what happens if I do that then? What do I have in the parentheses?
0.75 plus 1.
That's right. Very good of you. And now I can evaluate and say MC is going to be equal to 2.3 solar mass units divided by 1.75. And what's that net us?
Equals
1.3.
Sorry?
1.3.
All right. That's kind of nice. So the cold star is 1.3 solar mass units. If the sum of the masses have to equal 2.3, that kind of tells us what MH is, right?
1 solar mass unit.
1.0. Just keep precision the same.
Yep.
Okay, we're almost done. Now we can get the scale radii. We can get the scale radii by multiplying by the semi-major axis, which we now know is 0.1 AU. And the formula goes, the radius of the cold star is the scale radius of the cold star times the semi-major axis, and then we have to multiply by 215. That converts from AUs to solar radii. So let's try this together. Our original scale radius was 16%. So we'll do 16% times A, which is 0.1, times 215. And we'll call it 3.4 solar radii. The radius of the hot star can be found through the same computation. The radius of the hot star is the scale percentage of the hot star times the semi-major axis, and then we've got to convert from AUs to solar radii.
So
So our hot
1.7.
star, pardon?
1.7.
Yeah, so used 8%. So it's 8% times 0.1 times 215. Yeah. And let's take a step back and think about what we did here. The astronomers, now this was math, so I don't know how much fun you're going to think this was. But I went out and I measured some data points of a light curve. I basically measured how this one little star in the sky's brightness changed as a function of time. And I also measured some Doppler shifts. And what I now know are the relative luminosity of the star. I know that the cold star is more luminous than the hot star, but I've also gotten the masses of each star, and I've gotten the radii of each star. And at the beginning of our lecture today, I told you that what are the 4 most important parameters of a star? M, L, R, T. We now have the masses, we now have the radii, the temperatures we got from their colors, and we kind of got the luminosity. We got their relative luminosities. We'd have to use the distance to the star to get the actual luminosity. So binary stars allow us to get all the 4 properties that we want to know to understand the physics of a star. Cool. This is what you're going to be turning into me, class. Do we understand each other?
Yep.
All right. This is the sheet I want to get from you. Are there any questions? Can I help with anything?
Thank you.
Well, I enjoyed doing some binary star stuff with all y'all. And I can't wait to talk to you again on Thursday. Let's go to gallery mode for just a moment here. Before I end the recording, I don't know if there's any major things we need to talk about, but please make sure that you upload your labs in an easy to read format, JPEG or PDF. I should be able to see it. You should be able to see it in the window. That means I can see it in the window.
What's the lab name called?
LAB9, binary star orbits.
Yeah, I just called it binary star orbits because I was trying to be quick.
And I can upload a image, right? For some.
Yeah.
Yep.
Okay.
If you're using do you have an iPhone, Sal? Make sure you put your iPhone to most compatible format in your camera settings.
Yeah, so it uploads as JPEG, not.
That's beautiful.
Yeah.
That's all we need.
Just uploaded it.
Is there anyone that you know that's like here that did it wrong? Like, was mine an issue?
What's so hard about that, Michael, is not only do I have your class day and night.
That's fair. That's fair.
So it's like 80 people. And when I see someone doing it wrong, I'll be like, oh, Joey Bob, he screwed it up. But then two hours later, I can't remember who screwed what up. You know what I mean? There's just too many.
I was just asking if you had any off the top of your head. So that's cool.
No, but I try to let you guys know by putting a little comment there. So just go ahead and look at your grades there and you'll find out.
Got it.
Cool. Well, it's nice to have you all here. I'll be sure to upload these to YouTube and to Blackboard in case you need to look at it again later. How do we do on time? Are we? Whoa.
I have no idea.
Just about 2:30. It's 2:24.
Okay, so I took a little bit longer than anticipated there. Sorry about that. I think it was the technical glitches that stretched it out a bit. In any case, I'll stop the recording.
Dentist now because it's 2:30.
Huh?